Hello everyone, welcome. What we'll do is in the last class we have seen the application of direct stiffness method for analysis of truss. Today we will see how direct stiffness method can be applied to beams. The background that is required, that already we have discussed in first two classes of this week. Today we will just demonstrate how it can be applied and demonstrate the different steps in the application. Okay. So, let us see this example. This is a continuous beam, two span continuous beam. One end is fixed at A and B and C are roller supported, and then we have external applied load. All the dimensions are given here. Now, what we have to find out? We have to find out the we need to analysis mean we need to find out the displacements and then internal forces in the displacement, reactions and the internal forces in the beam. Okay. Let us do this. Okay. The beam is something like this. This end is fixed, this end, this is a roller support and this is a roller support, and then we have an externally applied load here 12 kilonewton per meter. Okay. And then this length is 5 meter, this length is 5 meter and this is 2.5 meter, 2.5 meter. Okay. Now, the next first step is the numbering of beam node and beam joint and numbering of joints and numbering of member. Suppose this is member number 1 which is, and this is member number 2. Okay. And then this is beam number 1, this is beam number 2. Then what we need to find, what we need to do, we need to name the degrees of freedom. You see, it has two joints, three joints, joint A, joint B and joint C, and at every joint we have 2 degrees of freedom. These degrees of freedom are vertical transverse displacement and rotation. Okay. Let us say in this case, so this is the problem description. Now, suppose this is the beam and this is point A, this is point B and this is point C, and then we have a vertical displacement here, degrees of freedom, vertical displacement and vertical displacement here, and then we have moment and then moment, right. So, at every node we have 2 degrees of freedom, total 6 degrees of freedom. Now, the numberings are, say this is 1, this is this rotation at joint C is 1, and then this rotation is 2, and then this is 3, this is 4, this is 5 and this is 6. Okay. Now, you could have numbered like this. This is 1, 2, 3, 4, 5, 6, something like this. It will be clear why I chose to number this rotation at this joint 1 and rotation at this joint 2. The reason is, you see, if you look at the structure, this is fixed end. There is no all the degrees of freedom are constrained here. So there is no translation, no rotation at this point. In this case, so there is no, in terms of displacement degrees of freedom, in terms of displacement there is no unknown here. Now, at joint B only there is no vertical movement, only rotation at joint B can take place. Similarly, there is no vertical movement at joint C, only rotation at joint C can take place. So, the unknown degrees of freedom in this case are rotation at point C and rotation at joint B. Just to make the unknown, if we number it 1, to when we say degrees of 1 is the first unknown, degrees of freedom 2 is the second unknown, it will help us while partitioning the matrix. Okay. Other than that, there is no specific reason for choosing this way, the numbering like this. You are free to choose numbering the way you want. Okay. As of now. Okay. So, this is the degrees of your numbering of the rotation and translation. Then what we need to do is, we need to find out we need to find out now element number, we need to find out the element stiffness matrix. Okay. Now, let us do it for we have two members, we need to find out element stiffness matrix for 1 and element stiffness matrix for 2. Now, if you remember, this is the expression for element stiffness matrix. Okay. That we have already seen. This is the member stiffness matrix. Now, how this member, what is this convention, this member stiffness matrix is written here. If we have a beam element, okay, suppose this is beam element, this is joint I and this is joint J, and the degrees of freedoms are like this. You have degrees of freedom, this is 1 and this is 1, and degrees of freedom, sorry, not like this. Once again draw it here. This is node I, this is node J, node I, node J. At node I, the degrees of freedom is vertical direction, and then this rotation, and node J, this is the degrees of freedom in vertical direction and then rotation. So, this is 1 and this is 2, this is 3 and this rotation is 3. This is the sign convention we chose. Please remember the way the stiffness matrix is derived here, they written here, the sign of the stiffness matrix is written here. This is the convention we used. Okay. And we have already discussed it in first two classes while deriving this matrix. Now, if this is the case, then this row is for this row is for, this is for 1, 2, 3, 4 and this is 1, 2, 3 and 4, right. So, if we take any beam element, so 1 and 2 is the degrees of freedom for first node if we go in this way, and the 3 and 4 are the degrees of freedom at second node, and the first degrees of freedom is the translation and the second degrees of freedom is the rotation. Okay. Now, if we now let us find out what is the now what are the things we need here for any element. We need 12 E I by L cube, then 4 E I by L, 6 E I by L square, and then that's what. So, let us compute these elements separately and then substitute in this matrix to get the element stiffness matrix. Now, for member 1, so first is member 1. Member 1 is I is this node number 1. Suppose this is node number 1, this is node number 2 and this is node number 3. So, this is node number 1, this is node number 2 and this is node number 3. This is member number 1 and this is member number 2. Okay. Now, for node number 1, I is equal to I is equal to first node, I is equal to 2 and J, I is equal to 1 and J is equal to second node. Okay. Now, let us calculate what is 12 E I, then 12 E I by L cube. L cube is L is 5 meter. So, this will become 0.096 E I. Let us write it in terms of E I. Then once we know the values of E I, we can substitute them, and then similarly 6 E I by L square is equal to 0.24 E I, and then finally 4 E I by L become 0.8 E I, and 2 E I by L becomes 0.4 E I. Okay. These are the things we need to calculate this stiffness matrix. Okay. Now, similarly, let us find out for joint member number 2. For member 2 span between joint number 1, joint number 2 and joint number 3. So, for member 2, I is equal to joint number 2 and J is equal to joint number 3. Okay. Now, similarly, we can, if we calculate them, then these values will be 12 E I by L cube, this becomes 0.768 E I. In this problem, it is assumed that E I is constant for both the both the span, but if it is not constant, you have to take that variation. Okay. So, this EI is for member number 2 and this EI is for member number 1, but here it is same for both the member. Then 4 EI by L, this become 1.6 EI, and then finally 2 EI by L, 0.8 EI. Okay. So, we have already calculated the elements of the member stiffness matrix for both the member 1 and member 2, and then what next we need to do is we need to substitute these values in this matrix, and to get the stiffness element stiffness matrix for both the members. And if we do that, then what we get is we get the expression like this. Okay. We get an expression like this. Now, you recall for member number 1, this was the member number 1 and this is the member number 1 and member number 2. Member number 1 and member number 2, this is the member number stiffness matrix for member number 1, this is the stiffness matrix for member number 2, and that we obtain by just substituting those values that we calculated just now into the member stiffness matrix expression. Okay. Now, one thing is important here, you see member number 1 span between, we assume that it is ith point and it is jth point. Okay. And ith point degrees of freedoms are 5, 6 and at jth point 4, 2, right. So, this is how if we remember if this is the stiffness matrix and the first column is these degrees of freedom vertical transverse direction, the displacement in transverse direction at ith point, and then second is the rotation at ith point, and third is the transverse direction at jth point, and fourth is the rotation at jth point. Okay. Now, then similarly, then for member number 1, degrees of freedoms are 5, 6. So, this is for 5 and this is for 6, and then for member joint number 2, this is for 4, this is for 4 and this is for 2. Okay. Similarly, along the row also, this is for 5, this is for 6 and this is for 4 and this is for 2. Okay. Now, for member number 2, spans between joint number 2 and joint number 3, degrees of freedom at joint 2 is 4, 2 and then 3, 1. So, this become 4, this is 2, this is 3 and this is 1, and similarly here it is for 4, it is 2, it is 3, it is 1. Okay. So, these two are member stiffness matrices. This numbering is very important, because the expression is, if this expression we have derived based on this arrangement of degrees of freedom, right. If you change the degrees of freedom, the numbering of the degrees of freedom, then this stiffness matrix will also change, and you have to use that accordingly. Okay. Great. So, we have these two member stiffness matrices. Then next step is to assemble these stiffness matrices. Okay. Now, for each member stiffness matrix, it is a 4 by 4 matrix, all are 4 by 4 symmetric matrix, because for every member we have 4 degrees of freedom, 2 translation and 2 rotation at both the ends. Now, when we assemble them, total degrees of freedom we have is 6, 3 joints, per joints 2 degrees of freedom. So, assembled stiffness matrix, the global stiffness matrix will be 6 by 6 stiffness matrix. And how to do that? The first step is okay. How to do that? Let us find the assembled stiffness matrix. Now, this is the assembled stiffness matrix. Okay. So, it is done for you. Now, let us see how this is assembled. The numbers are, this is for 1, this is for 2, this is 2, this is 3, 4, 5 and then 6, and again this is for 1, this is 1, 2, 3, 4, 5 and then 6. Okay. Great. So, 1 1 will be 1 point will be 11 here and plus 1 here. So, 1 here there is no 1. So, this will be 1 and then 1 is 1.6. So, it is 1.6. Similarly, 1 2 will be 1 and then 2 0.8 1 3 will be 1 3 minus 9.96 minus 0.96, 1 4 will be 0.96. Similarly, 1 5, there is no 1 5 here, there is no 1 5 here. So, 1 5 is 0, 1 6 is similarly 0. It is the same way we assemble the stiffness matrix for truss problem. The assembling is same, but the only difference is in the truss we had only the translation at 2 joints, here the one translation and one rotation. Okay. Now, let us see what happened to member number 2, then 2 1 becomes vertical, your column number 1 and row number 2. Column number 1 is this, there is no row 2 is 0.8. So, this become 0.8. And what is 2 2? Column number 2, row number 2, column is 2, row is 2 1.6, and then here also we have 2 and then 2.8. So, this become 1.6, this 1.2 to this 1.6 and then 2.8, 1.6 plus 0.8 and then this becomes 2.4. Okay. Then similarly, all other stiffness, all other elements of the stiffness matrix we need to find out. Okay. So, this is the global stiffness matrix for the entire problem. Okay. Now, once we have the global stiffness matrix, next we need to find out what is the load vector. Okay. Let us do that. Okay. Now, the finding load vector is, first what we need to do is, we need to first step is, if this is the problem, first step is we need to find out what is the fixed end moment for member number 1 and member number 2, and then calculate the equivalent joint load. Okay. Now, let us find the fixed end moments for member number 1 and member number 2. Fixed end moments are for member number 1, we assume these joints are fixed. Okay. And then member number 2, again we assume these joints are fixed. Okay. So, this is member number 1 and this is member number 2, and this is joint number 1, joint number 2, and this is joint number 2, and this is joint number 3, right. Now, this is subjected to, this is the load is, this is subjected to 12 Newton uniformly distributed load of 12 kilonewton per meter. There is no load on BC, on 2 3 there is no load. Now, what is the fixed end moment? Fixed end moment, if we know that for a fixed beam subject to uniformly distributed load, then the fixed end moment is W L square by 12, and the direction of this fixed end moment is, it is W L square by 12. It is okay, here it is here, and then reaction at the fixed end is this, and reaction at the fixed end is this. Okay. And there is then this value is W L square by 12, W L square by 12 become, this is W is 12 into L is 5, 25 L square by 12. So, this become 25 kilonewton meter, and this reaction becomes half total load divided by half. So, this become 12 into total length is 5 divided by 2 is equal to 30 kilonewton. Okay. Now, so this value is 30. I am not writing the unit here, this value is 30 and this value is 25 and this value is 25. So, this is the fixed end moments and or reactions. It is the reaction at the constraint bin. Assume the ends are fixed. Now, similarly, here also we can find out this is this, but there is no load acting on it. So, this value will be 0, this value will be 0, And what happened to the reactions? Reactions, this will also be 0, the vertical reactions, and this will also be 0. So, this is the fixed end, the reactions for the fixed beam. Okay. Now, the next thing is we need to find out the equivalent joint load. Equivalent joint load will be what? Equivalent joint load is just we have to sum the moments, and the opposite will be the equivalent joint load, right. So, to maintain the equilibrium at the joint. Now, equivalent joint load will be, then if we take this beam, this is, so at this point the fixed end moment is 25, which is anti-clockwise, and then the equivalent joint load will be 25 kilonewton meter, but it will be clockwise direction. Okay, 25. Now, this is 30 kilonewton upward. So, in this case equivalent joint load will be 30 downward. Okay. Now, let us see here equivalent joint load will be this plus minus this, the negative of this plus this, and negative of this plus this. So, total load here is 25, which is clockwise, then again 0. So, total load is 25 clockwise. So, at this point at point 2 your equivalent joint load will be 25, but anti-clockwise. Okay. This is 25, and similarly it is 30 here. So, this becomes 30 minus. Okay. At point C there is no equivalent joint load, because this is 0, this equivalent joint load is 0. Okay. So, this was node number 1, node number 2, and this is node number 3, right. So, then what is the so this is equivalent joint load. Okay. Now, next part is, once we let us look at the structure. If you remember, we know we have obtained the load vector, we have obtained the stiffness matrix, and then the stiffness matrix and load vector is related like this: K into D is equal to Q, right. K into D is equal to Q. Q is the load vector. Now, these generally we write like this, K. Now, in D is the displacement, the displacement vector, which has displacement at all the joints. So, it has K is a 6 by 6 matrix, D has 6 elements, the vector, and Q is also a 6 element, is a vector. Now, you see these ends are we know that all the degrees of freedom, all the displacement at point 1 are 0. So, means D5 is 0, D6 is 0, right. And then we know that D4 is 0, because there is no vertical translation, only rotation can take place. So, D2 is unknown, and then D3 is 0, because there is a support here, and D1 is unknown. So, only unknown displacements are rotation at 1 and rotation at 2, and all other displacements they are known and they are 0 here. Okay. So, we partition this matrix like this. So, this is we write D unknown and D known, and this is equal to, we write Q unknown and Q unknown is a Q known and Q unknown, right. And this is K11, K12, K21 and K22. This is how we can partition the matrix, right. This is how we can partition the matrix. So, what is D, what is Du, unknown vector, Du is unknown, sir. Du is equal to D2, D1 and D2. Du is equal to 1 is unknown and 2 is unknown, right. So, D unknown is D1 and D2, okay, and D known is D3, D4, D5 and D6, but these values are all 0, right. Now, let us see what happened. What about QK? QK q k known is what? Q k known is your which is q q1. You see, if we look at this, then q1 it is a roller support here, okay, extreme support, there is no externally applied load. So, we know that it will be 0 here, which is evident from this load vector. If you see the load vector, there is this q1, the corresponding to degrees of freedom 1, this is 0. So, q1 is 0, this is q1, and then this will be q2, and these are q1 is 0, q1 is 0, and what about q2? q2 is this value, this is 25, this is 25, okay. This is load vector 25. So, q k is known, and then what is q unknown? Q unknown will be, q unknown is equal to, it is same as we have done for next, up to this, up to getting the stiffness matrix, it is, there is a difference between different members, but once you have the stiffness matrix, it is just the solution of the stiffness matrix, and this procedure is almost same for irrespective of the structure you have. So, this is q3, these are q4, q5 and q6. These are essentially reactions at various joints, okay. But only thing reactions we know is, at this point the moment will be 0, because it is extreme end, and at this point it is in equilibrium. So, your equivalent load vector will be the q2, okay. So, this is 25. Now, what we have to do is, we have to now find out what is the unknown displacement. This needs to be determined, okay. Now, if we write the first part of this equation, then what we have? We have k11 into d unknown plus k12 into d known is equal to q known, okay. Now, d known is 0. Now, let us find out what is q11 and what is q12, that we need to find out from here. Now, the partition will be here is like this, partition is this. This is the partition. This is the partition of the matrix. So, this part is k11, this part is k12, k21 and k22. K11 is 2 by 2 matrix, k12 is 2 by 4 matrix, it is 4 by 2 and it is 4 by 4. Okay. So, k11 is this. So, let us write k11. K11 is it is 1.6, then 0.8, 0.8 and then 0.8 and then 2.4, and d unknown is d1 and d2, and plus k12 is this part, but dk is 0, the known displacement we have already seen that these values are 0. So, essentially these become 0. So, and this is equal to, and qk just now we wrote qk is equal to 0.25, and then we have 0.25, okay, 0 and 25. Now, if we solve it, then we get d1 is equal to, this gives us d1 is equal to minus 6.25 by EI, and d2 is equal to 12.5 by EI. Okay. So, this is the displacement at rotation at C and rotation at B. Now, rotations are obtained. Let us now we have to find out what are the unknown reactions. Now, unknown reactions will be, again, in order to get the unknown reaction, what we have to do? We have to get the second part of this equation. Okay. So, it will be d k21 into d unknown, k22 into d known. So, q unknown will be q unknown will be your q unknown will be this will be first is k 2 1 into d unknown d unknown plus k 2 d known. This is due to the now see total force, total reactions will be this total displacement will be displacement in this plus displacement in this, right. But since these ends are fixed, there is no displacement here. So, whatever displacement we get for this that will be the displacement for the entire structure. Now, now what would be the moment, what would be the forces, reaction forces? This will be the due to this and due to the displacement due to the displacement of displacement in this, and then whatever we have obtained here. So, now this will be, then this will be your this will be this displacement, this will be for the displacement in the second part, and then the next part will be your next part will be the whatever we have obtained for this. So, for displacement, let us find out first for displacement q obtained for displacement. You see k2 to d this is d known. Okay. Now, d known is 0 here. So, it becomes k21 is this matrix, k21 will be this part, this k21 will be this matrix, this part is the k21. So, this is minus 0.96 minus 0.96, then 0.96, 0.72, then 0, and then 0.24, and then 0 and 0.4, and d will be d1 and d2. Just now we have obtained this, and into this is minus 6.25 by EI, and this is 12.5 by EI, right. And this gives us this becomes minus 6, then 3, then 3, and then 25. Okay. But these reactions what we have, that is due to the displacement, that is due to the displacement. Now, what would be the total displacement then? Total displacement will be total reactions will be this plus for this. Now, let us find out this. So, total Q will be just now we obtained, that is minus 6, 3, and then 3, then 5, plus this is, if you look at this, this is 0, the first 0, then 30, then 30, and then 25. Okay. And this become is equal to, this is minus 6, then 33, then 33, and then 30. So, this is actually your Q3, Q4, Q5, and Q6. Okay. Now, Q3 is 0 here, that is why it is Q3 is 0 is the vertical reaction, that is why it is 0, and then Q4 was the reaction 30, that is why it is 30, and then Q5 was again reaction 30, that is why it is 30, and then Q6 which was the fixed end moment at joint 1, which is 25, and that is 25. Okay. So, this displacement, this is the contribution from the displacement here, and this is the contribution from the fixed end. So, total reactions will be this. This is how we can obtain the reactions. And the last part is, if you want to find out the forces in any member, say if you want to find out the force in member 1, we know the element stiffness matrix, and the force in member 1 will be the element stiffness matrix of member 1, element stiffness matrix in member 1 multiplied by the corresponding displacement, that would be the contribution from the displacement, and then plus there will be contribution from the from this. So, similarly we can, if you want to find out the member forces in this member, what we have to do is, the member forces in this member will be, let us find out for member 1. So, member 1 will be, for member 1, this is the stiffness matrix, this is the stiffness this is the stiffness matrix, and corresponding degrees of freedom is D5, D6, D4 and D2. So, this will be so member 4 so element the member forces will be, say, Q5, Q6 and then Q4, Q2. This is the internal force, that is the contribution from this. Contribution is K1 into D5, D6, D4, D2, and then plus what we have? We have this 30 at 0.5 at 30, D5 is 30 and this is 25, and again this is 30 and this is 30 and this is minus 25, because the way this matrix, this stiffness matrix are derived, this anti-clockwise, this direction is taken as positive, this is as negative. So, this is the contribution from the, if you look at individual member, this is the contribution from the displacement of the individual member, say in this case member 1, plus there will be contribution from this part, which we obtained by assuming the ends are constraint. So, these contributions are 30 and then 25, again 30 and then minus 25, and this become 33 and 30, 27 and minus 15. Okay. So, this is the forces in member 1. Okay. Now, quickly, similarly you can obtain the forces in member 2 as well. Okay. Now, let us see what is the, whether the forces that we obtain, they satisfy the at least this is the support reactions we obtained, Let us see whether these support reactions, they satisfy the equilibrium condition equilibrium conditions or not. Our beam problem was like this, okay. Now, so total reactions will be reaction at 1, reaction at 2 and vertical reaction at C. They should be equal to the internal total applied external load, which is 12 into 5 meter 60 kilonewton. Okay. Now, reaction Q1 already we have obtained. Q1 is, so Q1, so this Q5 plus Q4 plus Q3 should be equal to 60. Okay. Q4 is 33 and then Q5 is 33 and then Q3 is minus 6. So, Q3 plus Q4 Q5 total is 60, and here the externally applied load is 60. So, the results that we obtain, they satisfy the equilibrium, they have to satisfy the equilibrium, but only thing, it is just a cross check whether while doing the calculation, if you make some mistake, then this will not happen, the equilibrium may not be satisfied, that it is just cross check for that. Okay. So, so this has been a very small very demonstration by considering a smaller problem. You can solve any number of, you can solve a beam with different kinds of loading and any number of span, but the essence remains same. You have to divide it, get the element stiffness matrices, assemble them, get the global stiffness matrix, and then calculate the load vector, then partition the load vector and the stiffness matrix, calculate the unknown displacement. With the unknown displacement, you calculate the reactions and the member force. The steps remain same, only difference for different problem will be depending on the number of members you have to compute those many stiffness matrices, member stiffness matrices, and consequently your size of the global stiffness matrix will increase. But as far as the steps are concerned, it is exactly same that we have discussed now. So this was for beam. Next class we will demonstrate how the direct stiffness matrix, direct stiffness method can be applied to plane frame problem. Okay, I will stop here. See you in the next class. Thank you.